Hello, it's a pleasure to be presenting our work at this KDD workshop. And in this work, I would present our approach in making wind turbines more reliable through causal reasoning. Wind energy is becoming a popular source of renewable energy alongside solar energy and hydropower, as you can clearly see in this graph. However, wind turbines, they are becoming more complex and being deployed in challenging environments such as offshore with the days passing and years passing. And this leads us to lots of operational inconsistencies in the turbine, which require careful and challenging operations and maintenance to fix them or avoid the failures. And previously, historical work has used the data which turbines generate, as turbines generate lots of data from the different sensors involved in their subcomponents and measure the operational parameters in the turbine. And these have been used to train AI models which can predict faults with high accuracy. But unfortunately, most AI models at present, such as neural networks, they aren't able to provide the rational or transparency behind their decisions, which makes the turbine operators reluctant to adopt such AI-driven and data-driven techniques. And this work, we aim to bridge this gap, and we aim to identify causal associations in the SCADA data, that is the data which is generated from turbines, and develop temporal causal graphs so that the turbine operators, the engineers and technicians, they can easily look at these graphs and they can diagnose the corresponding relationships and find novel insights in the data. That's the goal of this work. Condition-based monitoring of wind turbines. So as I would refer to this as CBM, CBM has been popular, and we can look at this figure on the left-hand side upper corner, that power curve of the turbine. It shows that there are so many different types of anomalies, different types of faults and alarms which regularly occur in the turbine. And these are used to train AI models based on the corresponding mapping. So we have data generally in this structure. We have timestamp alongside corresponding features, and we have a label of the historical fault which occurred at that particular timestamp. So this is used to train the models, and we can get predictions of turbine faults and on anomalies with high accuracy. However, as these faults are challenging and they can share the relationships with each other. So you can see in this plot that there are many different types of classes of alarms which can be interrelated to each other. So one alarm can be a cause of the another, and there can be multiple alarms which share multiple causes. So that's also a problem. And there can be multiple types of faults as well. So in this study, we aim to use real world data from a real world turbine, and we would like to identify the hidden insights from this SCADA data in the turbine and generate a novel kind of decision-making approach for the wind industry. Why we really need causal reasoning? So as I mentioned in the previous slides, the wind industry, it's facing a challenging issue of operations and maintenance due to the challenging types of environments in which the turbines are deployed. And causal reasoning, it has historically shown lots of success in other domains such as medicine, finance, and other domains. And based on this, given that SCADA data from turbines is also highly complex and non-linear with maybe hundreds of features, we plan to use these features to identify the different types of relationships which take place in the data given a particular type of fault in the turbine. So firstly, before we move over to our proposed approach in using deep learning for causal inference, I would like to mention about traditional methods. So initially, we experimented with traditional methods such as the Bayesian structural time series for causal inference. And you can see that our goal here is to identify non-obvious relationships, because obvious we can easily infer. However, our goal here is to identify the hidden relationships in the data. So we found that initially such techniques, traditional techniques, while they were able to predict faults with high accuracy, they weren't really able to identify hidden associations. So we have an example here where the nacelle angle of the turbine, it affects the generator stator temperature in the component. So we can see that while there is a minor effect here, the model infers the relationships as mostly random and spurious. So it asked us that we should neglect this relationship. However, you would see that for the generator stator temperature time series, as an example on this graph, it really has a non-zero autocorrelation, which shows that it does have a temporal nature, which inspires us to look for alternate models, which can identify hidden associations, novel insights, and new things from our data, which we wouldn't have thought of initially. And we also experimented with another causal inference model, the deconfounder, which was proposed by Wang et al. In 2018. However, we found that the model also, it didn't identify the hidden relationships in the data, unlike the uh, hidden associations, which we would have liked to see in our approach for explainable and transparent decision making. This shows our proposed approach for causal reasoning. And causal reasoning through deep learning was initially proposed by this paper, Nota et al. In 2019 for other domains, that is neuroscience and finance domains. While you would clearly have seen from the previous slides that the wind energy domain, it faces a really challenging problem in operations and maintenance, and the data structure, that is SCADA data, it's significantly different from what we would notice in neuroscience and finance. So we modified the model architecture for our learning task. And the basic idea here is that we would have multiple SCADA features from the turbine. And for these multiple features, we would have multiple CNNs, so convolutional neural networks with attention. So each CNN with attention would provide us not only an accurate prediction of the corresponding univariate time series. So suppose the time series is wind speed, the CNN1 would provide us accurate prediction of wind speed. CNN2 would provide, suppose, accurate prediction of power output. CNN would provide us accurate prediction of pitch angle. So just imagine that scenario. And each CNN would give us also a transparent decision through attention scores. So these attention scores, or the kernel weights, which are used to identify the attention scores, they can provide us a good idea, good reasoning for causal inference. And that's the basic approach. And based on this graph, we construct a temporal causal graph, which can provide us the context of different faults which occur in the turbine. And from this, we can easily extract the different subgraphs for different types of faults to hopefully get more explainable decision making. Temporal causal graphs. So here we come to two examples I would like to discuss in this slide. So this is for an Yaw system anomaly. And as you can clearly see, there are so many different relationships which are identified through causal reasoning for anomaly in the Yaw system. However, I would like to mention about a notable relationship. That's the generator stator temperature and the Nessel angle, which the earlier traditional models had neglected as random and spurious in the previous slides. However, you would see that these are clearly related. And this probably occurs because the generator stator temperature affects the Nessel angle, and the Nessel angle is, you can see, directly related to the pitch angle of the turbine. And pitch angle, it is the angle at which the turbine's blades are rotated to ensure optimal production of power. So we can infer from this figure that due to an operational anomaly in the pitch system of the turbine, the power dynamics of the system are affected, which leads to fault in the generator. So this clearly articulates the things in a transparent manner. And what we observed is that we used a human evaluation for the identified hidden associations, and we saw that on average for all different cases, we got an approximately 55% of accuracy for different confounders based on our domain knowledge. So a second case discusses a pitch system anomaly, pitch control system, and this shows you a lesser number of relationships. However, we observed that lesser the relationships, more relevant they were, and more the relationships, conversely, they were less relevant. So we should balance this trade-off between identifying hidden associations and their relevance to our scenario. And you can see that pitch angle and active power, they are related. So it clearly shows that the pitch angle, it's affecting the turbine dynamics for the power. So a relationship P to Q implies that P is causally affected by Q. Similarly, you can observe a relationship between grid voltage, active power, and so on, which we found that it's quite relevant. And on evaluation, we observed that our model achieves a mean absolute scale error of 1.066, and it outperforms the baseline models in terms of MAC. Conclusions. So we conclude that deep learning based causal inference is promising for the wind industry, and it can significantly help us to identify hidden associations within our SCADA data. And the method clearly helps us identify hidden associations for different types of faults. However, it fails to identify some specific types of cases, such as wind condition alarms, wherein we only have few hidden confounders, and we would like to use maybe more data and combine optimization techniques with expert domain knowledge in the near future for this approach. And the clear graphical approach for visualization, it can be really helpful for engineers to identify novel insights which might have otherwise been disregarded in the case as noise. So that can be really helpful, and we aim to build upon this in our future work. These are the references, and we would like to acknowledge Catapult and University of Hull for this study. Thank you so much. It was a pleasure to present this work.